application challenges and opportunities will be presented by Dr. Mohamed, is a principal engineer, associate professor at the School of Engineering, University of Warwick in the UK. He joined Power Electronics Application and Technology in Energy Research Group to lead the team, which is well known in the application. He leads the team to develop the drive motor and inverter for the very hybrid electric vehicles. He has a wide academic and industry experience where he has taken different positions at the University Manufacturing Group in Belgium and Schneider Group in Egypt and Cairo University also in Egypt.
Thank you very much. Thanks for the introduction. Good afternoon, everyone. I think I have a little pressure now. We need just to finish on time because we are running out of time. So hopefully, inshallah, we will be able to squeeze the presentation within the time limitation. As we have the title of this presentation, which is talking about the silicon-carbide devices for automotive application. So today, we will try to give some hands-on the challenges and opportunities that we, in the automotive community, we are facing now while we are dealing with the silicon-carbide devices. We will go through this presentation by talking initially about the introduction and we'll take it step by step. So I know that the conference here have a good diversity of people from power electronics, power system, high voltage. So we will try to answer some basic questions. So for those who haven't seen or haven't dealt with the silicon carbide before, they can collect some knowledge about the silicon carbide and what are the opportunities that we can gain by using such devices. So we'll ask some basic questions like, why would we need some new power devices? We already have MOSFET, IGBTs, all these kind of devices. So why we are in need in something new? Then there is a common term which is called wide band gap that we keep hearing these days. So what is the wide band gap? And then we will go through a simple comparison between silicon and silicon carbide. And by finishing this introduction, we will go through the opportunities and challenges, some testing and reliability, and robustness lab equipment. Okay, so the first question, why would we need a new power devices? So in automotive, usually we have a magic word called requirements. And requirements in automotive is not coming from one way to another. So for example, if you are working in what we call it, the electric power drive train, you usually get requirements from everyone in the company. So I get used to work with Jaguar Land Rover for some time, and you are assigned your inverter to control the motor. But this doesn't mean that you're only responsible for designing the PWM or the control, the field electric control of the inverter. You have so many other requirements, something like what the Sam was talking about, the cyber security. You have to keep your inverter safe so no one will be able to hack the car, get the control of the EV. So a couple of these requirements actually come from the marketing team. So usually people who are working in the drivetrain, we are requested to provide the maximum power possible in the smallest space available. And the reason for that, if you look at one of the major OEMs at the moment, they usually keep saying that, okay, our car can go from 0 to 100 meters in this number of seconds. We have this amount of range, this car can go for 300 miles, and so on and so forth. At the same time, for the customers who do not know anything about the drivetrain, the motor inverter, they need to go into the car and they need to see it as big as possible. We need to give them a big storage space. We need the hood to be as big as possible. So this, by the way, put all the pressure on us to provide the maximum power or the greatest power that we can do, and at the same time all our devices has to be power dense. So you need to put this power within a very small amount of space. And the other thing, which is the efficiency of the system itself. And just to give a quick example for the efficiency itself, if you are talking about an electric vehicle that can go for 100 miles, for example, and you increase the efficiency of your system by 5%, or let's say 10% to make the math simple. So this means that instead of going for 100 miles, you will be able to go for 100 miles. So if you are competing with someone else from these OEMs, you can say that, okay, my car is going more in terms of the miles. This is one way, or the other way, that you can say, okay, we both having a vehicle running for 100 miles, but by this high efficiency, I can reduce the size of the battery. And by reducing the size of the battery, this means the reduction of the cost, so you can be exposed to more customers and can sell it more widely. So all these high level, what we call it high level requirements, it can be cascaded to us, and we have to fulfill all these requirements. And this is why the power electronics community or the drive community, you will keep seeing people trying to enhance efficiency all the way around. Okay? Although that you can see the inverters now 97%, 90, or even more, but you will find people trying to even go to much more higher levels. If you go one step back, for the inverters, we get used to have the PGTs, MOSFETs, and IGBTs. So PGTs, they managed to get the rating that we need, but they had suffered from low switching speed. The people started to go to use the MOSFETs, where you can get faster frequency, but the problem is the rating itself. The maximum rating that you can find in the market now is about 650 volt. So the next step was to try to find the IGBTs, trying to compromise between the benefits of the PGT as well as the MOSFET. And here, this is the next step, which is moving from the IGBTs, or the silicon IGBTs, to the silicon carbide components, which can be silicon carbide MOSFETs or silicon carbide IGBTs as well. So this is the whole story behind the silicon carbide. It's trying to get much more power, it's trying to get the system to be much more efficient, so we can fulfill all these type of requirements that we are getting from the other part of the system. Okay, so there is a quite known term now, which is the wideband gap. So silicon carbide is one wideband gap device, gallium nitride is C. So basically, the wideband gap is the amount of the energy that you would need for your semiconductor, okay, for one electron to move from the valence band to the conduction band, which is fine in terms of the device level, but for us, in terms of the application, what is going to benefit us? What I'm going to have from this? So if you go to this slide here, which is giving a quite summarized comparison between the silicon and silicon carbide, I would like to start with this rectangular shape here, which is identifying 4 or 5 different parameters in the comparison between the silicon and silicon carbide. So the blue line here is showing the capacity of the silicon carbide, and the orange one is for the silicon itself. So you can see here that in terms of the breakdown voltage, the thermal conductivity, melting point, electron velocity, and energy gap, all of them, the silicon carbide is much more higher than the silicon. But again, from the application point of view, what does this mean to me? Which we can see here in this table on the right-hand side. So if you look at the impact, so if you have higher energy gap and higher breakdown field, this means that your device can work out higher breakdown voltage, which means instead of working at 400 volt for the current EVs, there's a high demand now, a high trend to move from 400 volt to 800 volt, which we'll go through it in the next couple of slides. What are the benefits of this? We will go through it in terms of how much power we can run the vehicle, how can we expand different capacity of the applications that we are running through this. In terms of this thermal conductivity, this means that your device can extract all the heat within it quite fast and quite easily, which means that you can inject more power inside it without having problems with the thermal management. Thermal management is still not easy, it's a simple combine, but the device itself is giving you the capacity or the capability to work at higher temperature. In terms of the electron mobility and saturation drift, both of them are going to give us high switching frequency and reducing the RDS order, which is having a direct link with the switching losses and the production losses of the device. And by the end of the day, the overall system impact, you will be able to fulfill this requirement that we just mentioned about it, which is providing high power with lower size, which means your device is quite good in the power-based etc. Here is just a small example from Rome, and they are saying, if you have the same application and you are using the silicon and silicon carbide, you can see how much the reduction of the device when you go with silicon carbide. In terms of the application chart, and this chart is always quite common and quite famous for the people who are working with power electronics. You can see that, as long as your switching frequencies go, you still can work with the silicon, RGB, GTO, silicon. If you are higher the frequency, it is preferable to go with the GaN, but the rating is still not at the right amount at the moment. And this is where the area that the silicon carbide can cover at the moment. So we are talking about traction inverters around 400 kilowatt, and I can tell you that yes, currently in our lab we are talking about closer range to these values, which is around the 400 kilowatt. For the EV charger, in my opinion, I think the EV chargers will be one of the best applications that should be using the silicon carbide, especially if you are talking about wireless charger and all these kind of applications. Because one of the obstacles now for getting the EV through the different ways of convincing the customers to use the EV is a charging time. And if you manage to make very fast a charger or better charger, this means that people will be convinced to start to buy the EVs, which is already there in the European and UK advent. So if we start with this slide, so the silicon carbide is not new. It was there. But you usually need something to trigger the companies to start investigating or start working with this application. And one of the reasons that many companies started to work with the silicon carbide was the Tesla, when they started to use the silicon carbide in their Model 3. This is an image from the one of the legs, which was 2 times 14 silicon IGBTs in parallel to it. So by this time, there was not enough power modules, and this was one of the big debates up to now, that do we have to use discrete devices at TO247, or shall we go with the power modules, where we'll have all the dials inside one plastic box, as you will see in here. But anyway, for us, this is just to have an idea about the trigger, which made all the other OEMs to start thinking, okay, as long as Tesla is using this, so there must be some beneficial behind it. Okay, so in terms of the opportunities, based on these properties that we discussed right now about the silicon carbide, we all talking about efficiency and high power. So how the silicon carbide can reduce the efficiency, can increase the efficiency of the system and reduce the losses itself. As we all know that the inverter losses are either production loss or switching loss. And one of the benefits that we spoke about it regarding the silicon carbide is fast switching. So here in this example, something that one of our students has done, which is a comparison between a silicon MOSFET with a silicon carbide MOSFET with silicon IGBT. So you can see these curves here This is actually a turning on instance. So you can see the voltages coming, the orange and the red one is coming from almost 800 volt. And once you turn it on, it will go to zero. And you can see the difference in time between the IGBT and the silicon carbide itself. Below here, it's just again straightforward comparison when you use different gate resistance and when you calculate the switching energy itself. And usually this switching energy, you have the turn-on switching and turn-off switching plus the reverse recovery you get from the diode itself. Usually when you see this in microjoule, you probably say, okay, I mean, we are talking about microjoule losses, why this would bother me at all? But in order to get a real quantity, or I mean, to get a feeling with this, you need to multiply this by the switching frequency that you are going to use. So here's just a small example. If you are talking about application about 15 kilohertz or 50 kilohertz, and you can see the amount of the reduction. So here we are talking about almost 2% enhancement or 2% reduction in the losses when you move from the IGBT to the silicon carbide. Within the silicon carbide itself, there are different topologies, and actually this is one of the research that we are, it hasn't been published yet, but I mean, you can even think about different combinations. So we all know that the MOSFET itself has a parasitic body diode, that in most of application people keep using it. But even within the silicon carbide, this parasitic diode still have some switching losses. And what we tried here is to connect the Schottky diode in parallel with the MOSFET itself, and try to compare the amount of the losses in both cases. There are different other ways that we compare, but I would advise only to look at the comparison between the body diode and body diode with the Schottky body diode. So what we have done here, one time we used only the MOSFET as a silicon carbide in the application, then all the freewheeling would carry on through the body diode. The other one, we have physically connected a Schottky body diode in parallel, and you can see the difference in the losses in both cases. So again, this is one of the things that we, one of the opportunities that we can explore while we are talking about the silicon carbide. As I mentioned, I mean, there is quite high trend, and it is safe to say that most or all the electric vehicles will going to be 800 volt instead of 400 volt by 2025. And by moving from 400 volt to 800 volt, you can increase almost the power of the vehicle to double the size, or the other way around, as we mentioned, if we keep the power the same level, so you can reduce the size of the cables, you can reduce the losses and all the associated benefits with this. Okay, in terms of the high temperature, I think one of the properties we spoke about it also, that the silicon carbide can work at high temperature. So this means that the thermal management should be quite straightforward than the MOSFET itself. Although with all these opportunities, we still have some challenges. If you try to buy any silicon carbide MOSFET at the moment, you will see that it's still having a rating of the junction temperature at 150, 175 degrees. And the reason for this is not a limitation about the silicon carbide itself, it is a limitation of the packaging. Because people at the moment, the technology is there, but the packaging technology is not mature enough. So what they are doing in the industry now, that they are using the same packages that have been used for the silicon, and they are putting the silicon carbide inside it. So this is limiting actually the capacity or the capability of the silicon carbide. Okay, in terms of the challenges, we do have so many challenges starting from the fabrication. Fabrication itself, silicon carbide is not easy to be manufactured. For decades, people keep getting only 4-inch wafer. And I think in few years ago, they started to move to 6-inch. And now, as we can see, that people are going to 8-inch. Okay, I'll try to go more quickly. Due to these limitations or due to these challenges in the fabrication, we probably have some issues within the device itself. So in order to make sure that the device is working as it should be working, we have what we call it AQG 324, which is the qualification guidelines for automotive application. So basically, this is just a set of tests that your device has to go through it in order to say that yes, the device is qualified to be working within the automotive application. And the way that these qualifications is usually going, we usually get the line of the device, you characterize it, and then we go through the stress testing, then you characterize it again, and then you compare between the status before stress and after stress to see what's happening exactly within the device. This is just a couple of examples of the tests that we are going. Okay, let's go through. Okay. I think we missed a lot of this, but if we jump to the. Okay, let me just go through this in 1 minute. Okay, so these some of the equipment that we have in our lab which enable us to do all what we are talking about in terms of the reliability testing of the devices, even testing the overall system, which was all respect with all the sponsors up to now, but I haven't seen any of these equipment, which is something I think they can work on it if you are planning to write the scope that we are working here on it. So mainly, if for this type of testing, we would like to have environmental chamber, something like a thermal shock chamber, when you put the devices in distance. Okay. Just for all young colleagues here, we still have some opportunities in one universities. If anyone looking for PhD, you probably can approach me after this meeting, or if you want to